All right, let's jump right into this explainer. I want you to look down at your watch or just glance at the clock on your screen right now and imagine for a second that it is just completely lying to you. Today, we are going to absolutely shatter the illusion that time is some absolute ticking constant for everyone in the universe. Because, as it turns out, the fabric of our reality is far more flexible than that. Time itself can stretch, it can warp, and it can even freeze. Now, to understand the real world stakes of what we're talking about, we literally don't even need to leave Earth's orbit. 10 kilometers. Think about that distance for a second. That is the exact amount of error our everyday global positioning systems, the GPS you use to navigate to the grocery store, would accumulate every single day if they didn't correct for the relativistic effects we're about to dig into. Your map app would become completely useless in just a matter of hours. So this leads us to a pretty fundamental, really mind-bending question that's going to guide our entire journey today. What if time itself isn't ticking at the same rate for everyone? Answering this is going to take us from everyday technology, like our cars and smartphones, all the way out to the absolute most violent, extreme edges of the cosmos. To actually answer that, we've got to lay down some foundation with Albert Einstein's theory of special relativity. Now, the absolute key takeaway here is that the laws of physics are identical for everyone, no matter how fast you're moving. But since the speed of light is the ultimate cosmic speed limit, the one thing that literally cannot change, something else has to give when you start traveling at really extreme speeds. And that something is time itself. Traveling at high speeds physically causes the passage of time to slow down. Let's visualize this. Imagine a classic thought experiment with two observers. We'll call them Zoe and Jasper. So Zoe is in this highly futuristic, incredibly fast-speeding car, and Jasper is just standing stationary on the sidewalk. Now, Zoe has this special clock inside her car that's basically a light pulse bouncing straight up and down between two mirrors. To Zoe, sitting inside the car, the light just goes straight up and straight down. Simple, right? But from Jasper's perspective on the sidewalk, because the car is moving forward so fast, that light pulse actually has to travel a much longer diagonal path to hit those same mirrors. Okay, here is where it gets absolutely crazy, because the speed of light cannot change. It is rigidly constant for both Zoe and Jasper. The light in Zoe's car has to cover that longer diagonal distance from Jasper's point of view. So how does that work? Well, the only way the math actually adds up is if the actual ticking of Zoe's clock, the literal passage of time inside her car, slows down relative to Jasper. Let's actually put a number on this. Say Zoe's car is just flying at an incredible 80% of the speed of light. Because of the math behind special relativity, Jasper on the sidewalk would literally measure Zoe's clock as taking 67% longer to tick. To him, her time is just dragging. Her biological clock, her mechanical clocks, everything is running slower. But to Zoe, she doesn't feel a thing. Everything feels completely normal to her. Now, while special relativity deals with that extreme speed, we also really have to factor in Einstein's general relativity. This brings in the whole complication of massive objects and gravitational pull. See, it tells us that gravity isn't just some invisible force pulling us down. It's an actual, physical curvature in the four-dimensional fabric of space and time. And guess what? Just like speed, gravity slows time down. You can really see how this space-time curvature plays out here. We've got clock A sitting deep down in Earth's gravitational well, close to the surface. Then we have clock C, which is just floating way out in deep space, basically infinitely far from Earth's gravity. According to general relativity, because clock A is in that stronger gravitational field, it runs measurably slower than clock C. Gravity literally drags on time itself. And that brings us right back around to our GPS satellites. The trajectory of their net orbital time gain is just a perfect illustration of this. See, satellites in orbit are moving incredibly fast, which according to special relativity slows their onboard clocks down. But wait, they're also further away from Earth's center, right? That means they experience weaker gravity than we do down here in the ground, which actually speeds their clocks up. It's this wild cosmic tug of war. And it's exactly why we need continuous relativistic mathematical corrections, just so your phone knows exactly what street you're on. Now, we know for a fact this isn't just some mathematical fantasy, right? Because physicists have rigorously proven it over decades. It kicked off back in 1959 with the Pound-Rebka experiment. They measured gamma rays inside a 22.5-meter tower at Harvard. Then jump to 1971, and they're literally flying atomic clocks around the world on commercial airplanes. By 1980, they were launching hydrogen maser clocks straight into space on rockets. The crucial point here is pretty undeniable. Whether researchers were confirming the gravitational redshift of light in a brick university tower, flying commercial jets east and west to prove velocity and gravity dilation, or achieving this astonishing 70 parts per million precision in spaceborne rockets, we've seen multiple completely distinct environments perfectly and repeatedly confirm Einstein's predictions. And today, man, our technology has gotten so insanely precise, it honestly feels like magic. Researchers using these highly advanced optical lattice clocks in laboratories can now detect time running differently with a height difference of just 33 centimeters. Literally, time is moving slightly faster for your head right now than it is for your feet. Plus, this perfectly explains why short-lived subatomic particles called muons, which are created by cosmic rays way up in the upper atmosphere, survive long enough to actually hit sea level. Their incredibly high speed literally dilates their lifespans. Okay. Exploding outward from Earth for a minute, we've got to apply these rules to the absolute most extreme and violent gravitational environments in the vast cosmos. Because when you zoom out to this scale, the warping of spacetime isn't just a matter of microseconds anymore. It literally shapes the entire observable universe. Way out in deep space, we find these dead, incredibly dense binary stars known as pulsars. They spin ridiculously fast, basically acting as ultra-precise natural clocks. The gravitational fields between these binary pulsars are so intense that astronomers can actually measure relativistic orbital decay and what's called Shapiro time delays, where the actual curvature of space slows light down, with a mind-blowing error margin of less than 0.05%. And famously, back in 2015, the LIGO observatories actually detected gravitational waves from merging black holes actively warping the very fabric of space-time. But without a doubt, the ultimate climax of time dilation happens right at the edge of a black hole. We are talking about an environment so incredibly dense, possessing a gravitational pull so violently inescapable that the standard rules of classical Newtonian physics just completely and utterly break down. This brings us to the ultimate boundary of no return, the event horizon. Since gravity is essentially just the curvature of space-time, as matter gets closer and closer to the event horizon of a black hole, that curvature becomes practically infinite. Meaning, if you were a distant observer watching a clock fall toward a black hole, the gravitational time dilation is so immense that time effectively grinds to a complete frozen halt. You would never actually see the clock fall in. Its time would just stretch out into infinity. And that leaves us with a truly profound realization about gravity's influence, doesn't it? Time can stretch, it can slow, or it can effectively freeze altogether. From the simple map app on your phone to atomic clocks separated by literally a ruler's length, all the way out to the frozen precipice of a supermassive black hole, if the very fabric of our reality is really this pliable, whose watch is truly telling the correct time? Thanks for exploring the wild mechanics of reality with me in this explainer. Keep questioning everything.